Hi, this video we will talk about friction. So imagine when you put your hands together, you rub it, that there's friction, right? And when you push your car, and there's friction. So friction is everywhere. Now let's first look at a free body diagram. So I call it FBD, that means free body diagram. That is all the forces acting on this object. You're going to write it down. So in physics, you probably already learned free body diagram, and in statics, strength material, those engineering courses, we use FBD quite often. So this is represented in the book that is on the table. Okay, and let's put all the forces acting on this book. So first of all, we will have the weight of the book, right? And then we also have the table supporting the book, so that's going to be pushing it up. So put those forces up. And if we assume this is going to be acting in the center, so we will have the normal force pushing the book up. That's called the normal force. So that's at the vertical direction. In other words, it's at our y direction. This is our Cartesian coordinate, x, y. And how about x direction? Since what we are trying to do is we're pushing the force, so that's going to be this direction, right? I'm pushing the force going to the right. And however, the book is static, which means it's not moving. My force is not strong enough to keep it go. So in other words, there must be another force that's at x direction is trying to balance this force, right? Pushing this way. And so if we call this is F force, that's applied, applied force. And this force to the left is balance this one, and that's going to be our friction force. Okay, so in FBD, free body diagram, we're going to look at x direction and y direction respectively. At x direction, since this is static, which means everything is not moving. If it's not moving, it's going to be reach equilibrium. The left force and the right force have to be equal, right? Because we learned about some forces, all the forces, Newton's second law is F equal to ma, mass times acceleration. What happened during static? If it's a static, there will be no acceleration. Acceleration equal to 0. If that is equal to 0, what do we get for some of the other forces? That are going to be equal to 0, which means the left force and the right force at x direction have to be equal and have to be opposite direction, right? So at x direction, we have this F applied force. That's going to the right, right? So that's positive. And this friction is going to the left based on this coordinate, x positive to be to the right. And this force is to negative, so that's going to be minus this friction. All those have to be equals 0 because acceleration is 0. It's static. So in other words, you can figure out this friction force will be equal to the applied force if the book is at static, right? And how about y direction? Now let's look at the y direction, which is vertical direction. You have this normal force that's going upward, right? This normal force. So that's going to be positive because y positive is going up. Normal force is positive. Then you have this weight going downward. And going downward, it's at the negative y direction. It's going to be minus w equal to 0. So we figure out this normal force and the weight, they balance together. They equal. Okay. Now I invite you to look at this diagram. I'm going to draw X direction here is going to be this applied force we have over here. And Y direction is going to be our friction force. So from the first equilibrium at the X direction, we realize friction is going to be equal to applied force. This is when the book is not moving. When the book has not moved yet. Right? So in other words, this friction is always going to be equal to applied force. So let's see, if I start applied force at 0 and I continue to grow, here, for example, it's going to be 1 Newton. Okay? If I apply 1 Newton of force, what do you think friction have to be? Would that be equal to 1? Yeah. Then if I apply the force to be 2 now, what will be friction? 2. Then continue. Then you notice something during this area, underneath this area here, the friction is equal to applied force, and however, this friction is not a constant. So make a note, friction here is not a constant because it changes. It's going to be always have the same value of applied force, and applied force increases, right? It's not a constant. Then, however, when the book started to move, this is going to be reach this maximum point, maximum value, and this maximum value is going to be this value, F max is equal to mu n. We already know what's n. N is our normal force. Mu is going to be our friction coefficient, right? So coefficient of static friction. So let's make a note. Mu here is coefficient of static friction. Okay, so it reaches that maximum value. And then from our life experience, for example, if your car gets broken down and you're trying to move it outside to the curb, and when you push, which means you apply this force, for applied force, you increase, and the friction increases during that process because the car has not moved yet. So that friction is not a constant, it's increasing as your applied force increases. However, when it reaches this maximum value, mu n, mu being the coefficient of static friction, that's going to be determined by the car tire and also the road, the roughness, irregularity of the road, you know. And once that's reached, then when you continue push, do you feel like it's always easier, right? It's all, once it started moving, you feel like it's easier push. What happened here is once it reaches, and then the friction has a drop, and then it's become a constant line. During this process, is this area, we're gonna label it in a different color. This is when it's moving. When it's moving, we're gonna have this dynamic friction. And this dynamic friction is always less than this maximum friction. And this maximum is equal to mu n. Okay? So that's the whole concept of friction. So knowing that, I'm going to look at a quick example. So the example I'm going to look at is if this book on the table, they tell us this mu, the coefficient of static friction is 0.6. And they said the book weighs about 20 Newton. And the applied force is given as 10 Newton. Okay, so they ask, first question is, would the book move? Yeah, in other words, is this in this first region where it's static, or it's in this highlighted green yellow region where it starts to move? Okay, and then the second question is, what is going to be the friction force? So how do we solve this? First of all, we know the formula for maximum, right? Maximum force, or maximum, the point at this, right there, that's equal to mu n. Mu is 0.6, and the normal force. From our free body diagram, we already conclude at the y direction, the normal force has to be equal to weight because it's at equilibrium. The acceleration equal to 0, so normal force is equal to weight. So normal force is going to be equals weight as 20. And the maximum force will be 12 Newton. In other words, in order to get to this dynamic friction where it starts to move, we have to pass this threshold of 12 Newton. Then it can drop down. But what's our applied force at that point? Our applied force is only 10 Newton. If it's only at 10 Newton, what does that mean? Which means this book has not moved yet. This F applied is less than maximum. So it's still at this region, right? Because our applied force is right here. At 10 Newton, it's still less than 12, so the book has not moved yet. If it has not moved yet, what's going to be the friction? When it's static, we know the friction is going to take the same value as applied force, so the true friction at the time, it's going to be equal to applied force, and applied force at the time is 10. So from there you figure out friction is 10 Newton. All right, so that's our friction concept and the example. I'll see you at the next video. Bye now.